All right. Now, there we go. There's a little bit more I want to say about luminosity and apparent brightness before we move on. Okay. Now check this out. Here we go. Let's talk about units for a second. All right. I've lost my streaming. There we go. Okay. So let's talk about units for a moment. All right. Here we go. Luminosity. What's it measured in? Well, let me go back to this other page where I wrote the definition. If we look right here, the definition says the total amount of light energy produced per second. So it needs to be energy per second. Does anybody happen to know what the unit for energy is in most science? You may have heard this. You haven't heard this in this class, but you may have heard it in some other science class. Starts with a J. Starts with a J. It's joules. Joules is the unit of energy. Okay, joules. So here we go. Let me write that up on my page. Here we go. So luminosity is measured in joules per second. But you have seen joules per second before, okay? It's measured in joules per second. Check this out. Check this out. Joules per second is another name for a watt. Have you guys heard of watts before? Yes. A watt and a joule per second are the same thing. Where have you seen watts before? Where have you seen watts before? Yes. Yes. Light bulbs. Light bulbs always have their wattage written on them somewhere. So remember, luminosity is the total light emitted per second, which is measured in watts. So that means if you have a 200 watt light bulb, it's producing 200 joules of light per second. And a 300 watt light bulb would be 300 joules of energy per second. And that's why a higher wattage takes more electricity to run. Here's the problem though. We can't use watts. I mean, we could use watts for stars, but it's gonna be a pain in the butt, right? Why would watts be a bad thing to use to measure stars? Like the sun. Like if we wanted to do the wattage of the sun, why would that be a bad unit to use? That's correct. Stars are too bright and a watt is too small. If we were to use watts for the sun, the wattage of the sun is about 10 to the 33rd watts. The wattage of the sun is 10 to the 33rd watts. So yeah, even gigawatts is way too small. Watts are way too small. 10 to the 33, that's a 1 followed by 33 zeros. I don't even know what that number is called, okay? So instead, it takes a lot of light bulbs to equal the sun. Yeah. So instead, what we do is we make the sun's wattage the standard wattage for stars. And we call it, here we go, so this amount of watts is called a solar luminosity. And it's written like this. This would be 1 capital L circle dot. Let me zoom that in. There we go. So the luminosity of our sun is called a solar luminosity, and we make that the standard wattage for stars. So our sun is 1 solar luminosity, and that way we can deal with very small numbers. If there was a star with twice the luminosity of our sun, it would just be 2 solar luminosities. Does that make sense? 2 solar luminosities would be twice the brightness of our sun, okay? Or twice the luminosity of our sun. And with that in mind, the brightest stars out there usually don't get above around 1,000 solar luminosities. Usually, okay? So there are stars that are a lot brighter than our sun, but 1,000 is a number that's a lot easier to deal with than bajillion, jillion watts, right? So yeah, so luminosity is usually measured in solar luminosities, okay? Now, apparent brightness, apparent brightness has a unit that I do not like at all, okay? And that particular unit is called the magnitude. Okay? The magnitude. I really don't like this unit. I think it's a little out of date, and it's clunky and hard to understand, but it's used so often that I do need to teach you guys about it. Here's how out of date it is. The magnitude system was originally set up by a guy named Hipparchus. It might only be one P, but it doesn't matter. Based on that name, can you tell when this guy was around? When did this guy live? When did he come up with magnitudes? Like, if I'm Hipparchus, when am I around? This is an ancient Greek person. Yes, this is an ancient Greek person here. So, this system for apparent brightness is very, it's hundreds of years old, right? And technically, it's called the apparent magnitude. But I frequently just shorten it to magnitude. But here's the way it goes. Ancient Greeks didn't have telescopes, they didn't have cameras, so they decided how bright stars look just by what they saw with their eyes. And Hipparchus got a bunch of his buddies together, and they decided to classify the stars based on how bright they looked. And the absolute brightest stars in the sky were given a magnitude of 1. If they were the brightest stars in the sky, they were called magnitude 1. Okay? Now check this out. Magnitude 1 was the brightest stars. Stars that they decided were half as bright as the magnitude 1s were called magnitude 2. So magnitude 2 stars were half as bright as magnitude 1 stars. And then the stars that were half as bright as the 2s were called magnitude 3. And stars that were half as bright as that were magnitude 4. And half as bright as that was magnitude 5. And half as bright as that was magnitude 6. And then he stopped. So here's the question. Number 1, why did they stop? Why did they stop at 6? Why'd they stop at 6? That's right. If they kept going half as bright, 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 6s are extremely dim. And if you went half as bright as that, you can't see it with your eyes anymore. And that was the only thing the ancient Greeks could use. So that means the system stopped at 6 until we invented telescopes and were able to go see dimmer, right? So telescopes are able to see dimmer than your eyes. So now we have 7 and 8 and 9 and 10 on up. And can anybody see why I hate this? What is non-intuitive about this? What makes this confusing? Yes, bigger numbers, bigger magnitudes mean dimmer stars, okay? So if I discover, let's see if we understand this. If I discovered a brand new star and I told you, check out this star I found, it has an extremely high magnitude. What did I just tell you about that star? If I told you my new star had an extremely high magnitude, what am I telling you about that star? So if I say it has a high magnitude, I mean that the magnitude is a very high number, which means that the star is very dim, okay? So if I say a high magnitude, 6 is a high magnitude, 1 is a low magnitude. So a low magnitude means a bright star, and a high magnitude means a dim star. I don't like it. I don't like it. It's confusing. Let's just put like a big frowny face on this. Oh no. And write the word flipped. Maybe over here we can write low is bright and high is dim. Okay? I hate it. I hate it so much. I wish we would get rid of it. I also am not a super fan of the half thing. But, you know, that's a different issue. Okay? But essentially, I'll go ahead and tell you right now that this is going to be one test question about magnitudes, okay? There's going to be one question about this, and it's going to be designed to make sure that you know it's flipped. So essentially, you're going to have a situation on the test where there's one object that's bright and one object that's dim. And I'm going to ask two things about it. And we got to be careful here, okay? So imagine thing A is bright and thing B is dim. If I ask you which one has a higher apparent brightness, you would say the bright one has a higher apparent brightness, okay? So the answer to that one would be A. But, here we go, but if I asked you, remember, A is bright, B is dim, if I asked you which one has a higher magnitude, which one would be the answer? Which one would have a higher magnitude? Bright thing A or dim thing B? Dim thing B. That is correct. So again, if I told you bright thing A and dim thing B, you would tell me A, the bright thing, has a higher apparent brightness, but B, the dim thing, has a higher magnitude. Okay? I'm just telling you right now, that's going to be a test question. Write it down. You'll be good. All right? Okay, I think I have a question here. Somebody is asking if there are intermediate magnitudes. There are. It's not something you have to worry about for a test, but yes, there would be a 1.5 and a 1.7 that would be in between these two brightnesses right here. Okay? In between each of these magnitudes, you can have more of them. And by the way, the Hubble Space Telescope can see all the way to a magnitude of 30, which doesn't seem like a lot dimmer than what your eyes can see. But remember, every time you go down a number, or I should say, every time you go up a number, you get half as dim. And so that's a half times a half times a half times a half times a half 30 times to get to a magnitude of 30. And so that means the Hubble Space Telescope can see millions of times dimmer than the human eye. That's why every time we invest in a new telescope that can see a higher and higher magnitude, every time we add another magnitude to the telescope, we're able to see way dimmer objects, and we always will be discovering new stars and new galaxies. There's a replacement for the Hubble Space Telescope that's going to be going up soon-ish, probably sometime in the next 10 years. And when it does, because it will be able to see a much higher magnitude, it will almost instantly be discovering millions and millions and millions of new galaxies. So look for a bunch of new galaxies to be known very shortly when we get that new telescope up. So yeah, that's pretty cool. All right. Okay.